Okay, thanks everyone for coming. Thanks everyone online. Yeah, for those that are newish, maybe most of you, I used to do these kind of lunchtime talks, kind of background DAAC scientist talks, and kind of stopped doing those when COVID came around, and kind of have been lazy and restarting these. It's been kind of on my mind to do. So this will start hopefully about once a month or so. I decided to start with basics of remote sensing. I will say this is really basic. If anyone's had a remote sensing course, you may be pretty bored by this, apologies. But kind of a good overview, kind of, again, focused on kind of the things that we do here at NSIDC, giving kind of basic background information if you're not familiar with certain things. So, okay, so I always like to start out with the history a little bit. This is what 64 years ago, the Tyros-1 satellite. That was the first environmental satellite, Earth-looking satellite that was launched. So about 3 years after Sputnik, I think, right? Sputnik was 1957. So this was kind of the beginning of Earth remote sensing. This is the first image on the right ever taken by of the Earth from satellite. An interesting story here. I'm not sure if it's apocryphal. It may well be, but it's a good story. But they, this was the space race, getting things up. They got it up there, and they threw it and got the camera and take pictures. And here comes the pictures. Like, cool. And then it's like, what is that? They didn't have, supposedly they didn't have geolocation on the imagery, at least initially. So they didn't know what they were looking at. So they got a picture of the Earth, but it's like, what is that? I don't know. So again, that might be apocryphal, but I like the story anyway. So remote sensing is based on electromagnetic energy, which comes through electromagnetic waves, or that's one of the ways of looking at it. And the waves these are characteristics. It's got an amplitude, height of the wave. It's got a direction, which way the wave is flowing, which I didn't put an arrow on there. It's moving at the speed of light. Remember, it's not just a suggestion, it's a law. Speed of light, they're in a vacuum. The wavelength is the length between the peaks or the troughs, basically the one cycle, and frequency is the number of cycles per second, how fast the wave is moving, given in hertz or 1/2. Speed of light is the frequency times the wavelength. That's what speed of light is, and then there's a wave number that I won't talk about, but that's just for reference. That's another way of describing it. So you can describe either wavelength or frequency, and depending on the type of remote sensing and what channels or what part of the spectrum you're looking at, sometimes it's wavelength, sometimes it's frequency. Technically, they're interchangeable. So the electromagnetic spectrum spans wavelengths from tiny nanometers and so forth, essentially all the way up to really large scale wavelengths. It's basically emitting in all wavelengths. So long waves have lower frequency, lower energy. Short wavelengths, higher frequency, and then at higher energy. So you get onto the, that works. A high frequency, very short wavelengths. You got X-rays, which penetrate through soft tissues, gamma rays, but then on the longer radio waves, which are great because they transmit information like your radio, your television, and so forth, but they're not harmful because they're low energy. Put down here a couple. This is in the microwave radar range, because we have a lot of data that's microwave data, and it's in gigahertz, which is 1 × 10⁹ hertz. 1 gigahertz to 100 gigahertz is kind of a typical range, especially for Earth surface remote sensing. Some of the atmospheric sensors have higher frequencies, but just kind of pointing that out for reference there. All right, so everything above absolute zero is emitting electromagnetic radiation. And we talked about black body radiation, which is basically if it's emitting perfectly, it's emitting all the energy that it possibly could. And that's a function of the temperature. So the temperature gives you basically the wavelength of the frequency at which the body is radiating. It has a black body. So the sun is 77 Kelvin or thereabouts, which puts it in the visible spectrum, the visible range. And that's the part that we can see with our eyes, which is very convenient. Otherwise, we wouldn't be able to see anything. The Earth is, of course, not near as hot. It's more around 300 Kelvin. So it's way out, its peak wavelength, emission wavelength this is in micrometers, is at around 300 Kelvin. So it's about 10 micrometers that it's emitting at. I'll talk a little bit more later, but that's well beyond the visible range. We don't see that energy. But that's actually in the infrared. It's getting into the heat. That's the heat that we feel is the thermal energy coming from that as again, this is the assumption as a black body, which isn't perfect, but it's very useful. So again, this is the peak curve for the sun. This is in the visible range, and then the Earth way out in the infrared. I'll mention microwaves I talked about, and again, we have a lot of microwave data. That's like way out here. So that's a much lower energy. There is, the peak is not visible on this scale, basically. So it's really very low energy. And it's a very low temperature that it's emitting at. And we can use that. This is just an interesting, this is not earth science, but I think it's interesting. This was I think it's the WMAP, Wilkinson Microwave and that's anisotropy probe that looks into deep space. This is one of the sensors that looks back, and it's detecting microwave energy at 3 Kelvin, which is the cosmic background radiation of the universe. And by looking back, it's basically seeing the universe as it was just after the Big Bang. I forget how long it may even be minutes, I forget, but it's like the remnants of it. And when they looked at this way back, you see all these different patches. They didn't put a color scale in, but it doesn't really matter. But you see, it's not like nice and smooth and uniform or symmetrical. It's got these blotches. That's basically what leads to that those blotches have gravitational force and start pulling things together. That's what formed the galaxies, and eventually suns and planets and so forth. So the fact that it wasn't uniform caused these things to pull together. So I don't know, I think that's kind of an interesting, again, just a little aside there. We look at the spectrum of solar radiation. We can actually measure the actual amount of radiation, and you can see it's not actually an ideal black body, which is this nice smooth curve here. And this is again the sun's energy coming to Earth. There's the UV light, which we all know from sunburns and suntans, visible that we can see, and then out into the infrared. So the yellow is basically at the top of the atmosphere as it hits the atmosphere. So that's everything coming from the sun. And then, of course, going through the atmosphere, some of it gets reflected or absorbed. And then you end up with at the surface, the red, essentially. And so certain wavelengths get absorbed by the atmosphere. You can see down here that where really no energy gets through because the atmosphere is absorbing it or reflecting it. And so the red is what gets through. So we get, not as much energy as the sun actually provides. This is another one that this is looking at the Earth. So this is the solar energy coming in. This is the Earth's emitted energy now. So this is going out from the Earth. The Earth absorbs the energy from the sun, and then it re-emits that energy again, more in the thermal band. This is 10 microns. There is the peak, but you see, you don't have this nice, you have the idealized curve here, the black body curve, but you see there's a lot of gaps there. And that's because the atmosphere is absorbing the energy as well. So the Earth emits energy, some of it goes up to space, but some gets absorbed by the atmosphere and the particles in the atmosphere. And one of the major one really is water vapor is the biggest absorber. But one of the key ones that we probably all are familiar with is carbon dioxide. You can see here, this is carbon dioxide where it's basically absorbing everything at those wavelengths, and so it's absorbing the energy, and that's the greenhouse effect. That's one of the primary drivers of the greenhouse effect with the carbon dioxide. There it is. We also get scattering. That's what gives us haze. The particles in the atmosphere scatter, whether it be from smoke. This is an image from Boulder. I had this in an old slide and I don't remember when it was exactly, or even I might have taken it. I can't remember, so I apologize to anyone I may have taken this from. But you can see you're looking towards the flat irons and you don't really see them. And of course, we've experienced this here on many occasions. So when we are looking at satellite data, of course, we're above the atmosphere. So we're looking down at the Earth from above the atmosphere and detecting the electromagnetic energy that's coming into the sensor. And so you get, emission from the surface, you get reflections, the sun's reflection from the surface, or even below the surface, especially in the oceans, can penetrate and then reflect back. You get atmospheric scattering and atmospheric reflection, clouds, aerosols, and so forth. This is clouds actually emit too. So you have the emission from the Earth's surface, emissions from the atmosphere, and those are all coming in to the satellite. And of course, when you are looking at remote sensing and wanting to use it to investigate the Earth, you don't necessarily want all those things, and not all the sensors are going to address all of those. So you can, design sensors, and that's what's done to look at exactly what is of particular interest. A little divergence into satellite orbits. When satellites are in orbit around the Earth, the orbits are very important for what gets seen. It's looking down, and so where the satellite goes is important for what you see and where you can get data from. And so it's it's in orbit. The gravitational force is essentially the thing that's controlling the orbit. The interesting thing, there's a lot of equations with this, but the key thing is in this velocity here. This is the gravitational constant, the mass of the Earth, the radius of the Earth. Those are all essentially constant. So the only thing that changes is the height. The h is the height above the Earth's surface. So the speed of the satellite is a function of the altitude above the surface, and only that. And then the period is the time to complete a full revolution, which again is of course dependent on speed. So I point out a few orbits that are of particular interest. The first one is the geostationary orbit. Essentially, again, your speed is dependent on your altitude. At a certain point, you can get the speed being the same as the Earth's rotation speed. And so the satellite sits at the same place over the Earth. Geostationary has to be over the equator, and then it will stay exactly in that spot. There's geosynchronous, which is a more general, which can move up and down across the equator, but still goes along with the Earth. So it has a period of 23 hours, 56 seconds. So this is where like the standard, your GOES weather satellites are, because then you can look down and you can see the weather systems as they're evolving continuously. Communication satellites, that's obviously important so you can keep communication, but they must orbit at the equator to be geostationary. It also, I didn't put that in here, but one of the things that is a limitation for these is because they're at the equator, they can only see so far to the north and south. So they don't see the whole Earth. So in high latitudes, near polar latitudes, you don't get data from these. And I also mentioned, so it's 35,700 kilometers is that point where the speed is the same as the Earth's rotation. Did you have a question?
Yeah, would that also be like navigational satellites?
So like GPS, like navigational, they have a different way of doing things. That's one way to do it, and I think they have done that in the past, but GPS is a better, a different approach. And what they do is they just put a whole bunch of satellites up, and they're always orbiting around, and you're always within, they put enough up so that you're always within 3 satellites in view. And that means you can triangulate and calculate, and the advantage, a major advantage there, as I understand, is that they're a lot closer to the Earth. So if, 22,300 miles, it takes a while for the signal to bounce up, go up and then bounce back. So being closer gives you faster and more accurate information. So, and the triangulation also gives you more accurate information too. Yeah.
Is there something about the height of, like with GPS, like not being as good, like at higher elevations?
I'm not sure what,
Yeah.
I don't even remember what
So,
altitude they put for those.
Usually the signals come from the GPS satellites to your receiver, it's only one direction. And what your phone or any other GPS device that has a model of the Earth.
Yeah.
And that's where the height discrepancy comes in
Oh,
place.
okay,
It's a reference thing.
Yeah,
yeah,
yeah.
okay.
So I don't know if there's if they chose a height in particular, or what the optimal height is.
Right, the Earth is not perfectly sphere, basically.
Yeah. Yeah, good question. So this is the geostationary, I just showed, this was just an example, this was from the 21st of January, you can kind of see, doesn't show up well, but this is like this. This is the snow storm that hit the south yesterday, it's the Gulf there.
Wow.
Yeah. So, but you can see here, you can't really see the poles very well, this is Hudson Bay, and that's about as far as you can really see anything, so you don't get much data in the poles. So the other orbits, really class of orbits, polar orbiting, and these, like I say, go over or near the pole. And the value of that is that you can see the polar regions. You can't see those with geostationary satellites. So there's the polar orbiting satellites, and this is what we have a lot of at NSIDC, are polar orbiting. Certainly the majority of our data comes from polar orbiting satellites, not all of them, but this is just a snapshot. Yeah, this just shows there's like SWAT, Landsat, SMAP. We have the SMAP data. Yeah, there's a couple others. There's that Grace. Yeah, the GPM. So there's a lot of these. This is tropics, which I forget what exactly that. Essentially, that's a NASA sensor though, but that's not polar orbiting. You can see it's kind of lower. There's a neat animation. I didn't put it in because it's really huge, but if you go to NASA, you can find the updated, I think they update it now daily, basically, of all the NASA satellites or NASA related satellites. Anyway, so one of the polar orbits that's particularly useful, and is a very special polar orbit, is, as the satellite is orbiting, the Earth is turning underneath. So every time a polar orbit goes around, and that's a limitation of polar orbits, is that you're only seeing part of the Earth on each orbit, and you have to kind of composite things together to get a full picture of any location. But as the satellite's orbiting, the Earth is turning. The Earth turns about 15 degrees every hour. 24 hours, 360 degrees, that's 15 degrees per hour. So you can design an orbit such that as the Earth turns 15 degrees, the satellite basically crosses the equator 15 degrees. The orbital period is such that the Earth is turned 1 hour and it's coming back across the equator at the same local time at the equator. So essentially, you get data, at least at the equator, at the same time of day, local time, every single orbit. And that's called a sun synchronous orbit. And it also, the Earth precesses, it slowly rotates as it orbits around the sun, right? So you have to adjust for that a little bit. So it's not exactly 15 degrees, but this is really useful for if the sun angle is important to your data, because the sun angle affects, like, reflection is dependent on the sun angle. And then diurnal effects, like if you're tracking snow, it may make a lot of difference if you're seeing the earth at 6 AM when it's cold versus like 4 PM when the sun's been melting in the snow for a long time, or crops and things like that. So you can design these orbits and set up, and that's done with a variety of different satellites. They have different crossing times, because they oftentimes have like a morning and evening crossing time, like MODIS. The passive microwave like Amser, and they do that, so they can capture, they can kind of capture a diurnal effect there. This is another example, just showing this. Again, the altitudes are typically around 700 kilometers, 700 to 800 kilometers. Period is about 110 minutes. And then they go, even retrograde, which means they kind of go backwards. So they're kind of going against the grain, so to speak, of the Earth's rotation. And again, we have lots of satellites at NSIDC. Notably, ISAT-2 is not sun synchronous. It is a polar orbit, but it's not a sun synchronous polar orbit. So you have the geostationary is really cool. This is just another interesting orbit. The geostationary is really cool because you can see a certain location pretty much continuously, but you can't see the poles. You got the polar orbiter, you can see the poles, but you can't see it. You can only see it once every 90 to 100 minutes or so, and you don't see it in the same spot. But there is a polar orbit that comes really close to a geostationary orbit, and that's thanks to the Russians. And so, the orbit velocity, function altitude, the lower you are, the faster you move, the higher you are, the slower you move. So they developed this, what's called a millennia orbit, and it's a highly elliptical orbit. So it basically, you're up here, this is by hour. You come up here, you're moving very slowly, so you're hanging around above the pole for quite a while, and then you shoot around really quickly on the other side. And so if you have three of those, you can kind of have continuous coverage of the poles. We don't really have millennia orbit satellites. The Russians have done it. Canada has talked about doing it because Canada being in the far north. Russia, it makes sense because they're in the far north. They don't get as good of use of the geostationary satellites. So, but it's kind of interesting. So they're like a 12-hour orbit. So again, you get 2 or 3, you can kind of cover that. Oh yeah, one final one. I think is kind of interesting. It's in a sense, it's not really an orbit, but it's a satellite that sits at what's called the L2 Lagrange point, which is, you can see here, it's actually beyond the Earth. It rotates around this point, and it's where the sun's gravity and the Earth's gravity kind of cancel each other out. And so it can sit essentially in one place or orbit around a stationary point. And that's really useful, obviously, for something you want to keep away from the Earth and have a stable point. So for example, the Webb Space Telescope, that's where that is at, because you want it away from the Earth, away from any other sources and looking up to space. It's also the Discover EPIC satellite. And it's actually about 1.5 million kilometers behind the Earth, and it's a stable position. There's other Lagrange points, and those are not stable. So stable means like, you're going around and it gets perturbed a little bit. It will kind of bounce back to where it was. Whereas an unstable one, if you lose your position, you start spinning off into who knows where. So you want a stable one. So this is this is a little animation. This is the solar eclipse from last year, from the EPIC. So the EPIC is looking at the Earth from about 1.5 million square kilometers away. And that essentially gives you a full disk. So you actually can see the poles from this. And it has a lot of sensors on it. This was also has a solar observatory. So the one side is looking at the sun, the other side is looking at the Earth. And this was has been known as Al Gore's folly. Not to go into too much of a diversion, but he suggested this back in the 1990s when he was vice president. When that administration ended, this basically got shelved because they didn't want certain people did not want an Earth looking satellite. Essentially, the idea, one of his ideas behind this was you had the Earthrise and the blue marble images from the Apollo. We hadn't actually gotten those anything like that since then, and that was kind of the awakening of the environmental movement. And so Al Gore had this idea: we put a satellite up that had pictures like this, and you would instill. That was one of the rationales for it. Again, certain people didn't like that idea, so it got shelved for many years. Eventually, it got launched. There was actually talk. One of the reasons it ended up getting launched is because they needed a solar observatory. They need you want to know what's happening with the sun if there's a solar flare, things like that. And this was ready and available. There was actually talk of like stripping off the Earth looking sensors on it, because they're like, okay, we need a solar one, but we don't want this other stuff. But eventually it did get launched under the Obama administration. I forget exactly when it was. And it's collecting data. So interesting point. So ground track is what the satellite sees. This is what it's looking, this is what it's going over. The sensor may see more, but this is the actual point of the Earth that it's going across. This is an ISAT-2 ground track. Kayla is very familiar with this. You may recognize that. And so this is from Open Altimetry. And so you can see again where it's collecting data from, or where it's flying over, and then the polar look there. But again, the sensor is capturing, depending on the sensor, it's going to capture not just right underneath it, but a certain width, which is called the swath width, and that provides the coverage that you see. And depending on the type of sensor, you get different types of, or you get different swath widths. This is MODIS from Terra, and you can see, there's these little black areas. So that's where the sensor, this is between swaths as the satellites move around. So there's a data gap there. If you have a wider swath, which actually veers as a wider swath, you don't have that gap. Of course, if you get to the poles, there's more overlap, and so you don't have those gaps there. All right, so types of remote sensing. Passive remote sensing means that the sensor is passively receiving energy. It's not sending out any energy itself. It's just capturing the energy, either reflected or emitted by the Earth or the atmosphere. And so they are just basically looking at, like a couch potato sitting there looking down and collecting the energy. And then active remote sensing means that it's supplying its energy. It's sending out a signal. That signal is going down, it's hitting something, it's reflecting or scattering, and then it collects that reflected energy and recovers it. So those are two different ways of getting information about the Earth from remote sensing. And ISAT-2 is an active remote sensing. It's a LiDAR sending a laser out. And then we also have laser cams. I don't know if they're actually being used for remote sensing, but they're kind of cool though. So visible infrared sensors, I put these in the wrong order. We have a history of these going back to AVHRR was, and there's earlier ones too, but kind of the main ones. AVHRR, Advanced Very High Resolution Radiometer. This was basically succeeded by MODIS, which is Moderate Resolution Imaging Radio Spectral Radiometer. MODIS at moderate resolution is much higher resolution spatially than the Advanced Very High Resolution. Ironically, that is giving a little sense of the change in technology, I think. And then the most recent is the VIIRS suite, Visible Infrared Imaging Radiometer suite. And there's Landsat is a kind of a special, it's visible and infrared. It's got very high resolution, but looking at smaller areas. And then there's a lot of commercial and military sensors out there as well. So I won't go into very much detail here, but basically these have different visible channels and then infrared, either we'll call near infrared, which is still reflected energy, primarily, and then thermal, which is the emitted energy, the heat essentially. And so they have various different channels. Some of these are, they use like several channels that have very close wavelengths that can help kind of filter things and get better data. but the general central bandwidth there. And these are, again, the central values. There is a spread of the energy that it's getting. It's not only that one number, and that bandwidth can vary, but that's what's typically used. And so you've got red, green, and blue, and then these infrared channels. So this is a Meier's True Color Composite, 18th of January. I grabbed this, I think this was like one of our snow events there. That's somewhere around here is Colorado with the white snow. And so this is from the Worldview, NASA's Earth Data Worldview site, which is really quite convenient, quite nice. It updates as the data come in. So you get basically near real time or close to near real time imagery. And this is a True Color Composite. So if I talk about that, yeah. So it's designed to, like, it uses red, green, and blue, which are the main colors that, go into a composite. And, but, so it looks pretty realistic, but it's not exactly, our eyes our true color, the eyes that we see with our eyes is the entire spectrum. Whereas Modis or Meier here is looking at specific bandwidth and specific channels. So it's compositing those to make it look like it's pretty close, but it's not exactly what we see. So yeah, when we look at this, it's not exactly telling us the complete truth, but it's pretty close, very useful. And then this is a polar look. Colors are a little washed out there, but Antarctica on the right and the Arctic. This is a visible true color, so when it's dark out, it doesn't see anything. So blocks that out. All right. So vegetation, of course we can see vegetation, it's green. But it also has emits it reflects in the near infrared as well. And it's actually that which we don't see, but it's that we can use to look at the density and the type of vegetation. It's basically a difference in the reflectivity, which is called NDVI, there it is, yeah, normalized difference vegetation index. So again, it's basically using different channels, and this is what's typically done in remote sensing. You're using different channels, combining them to look for physical properties that have those characteristics. In this case, it's the near infrared and the red, and it's a pretty simple, just basically a normalized difference between those, and tells us basically how lush an area is, how much vegetation. So you can see Africa here, the tropics, the tropical forest, very dense vegetation, and then the Sahara is the extreme contrast the other way. If you look, kind of over here, the little thin ribbon, that's the Nile. So you have the Nile River, we have vegetation along the river, but nowhere else. Yeah.
Question for you. So the green that curves around the southern end of Africa on the east side, has that got to do with ocean currents or atmospheric circulation, or?
I would say probably. I don't,
Okay.
for sure. This is the Namib Desert here, I think.
I think so.
Yeah, and so, yeah, it's basically getting moisture, that's supplying vegetation, probably due to winds coming up off the ocean surface. Yeah, yeah. Okay, so we can also look at ocean color. You think, well, the ocean's blue, right? But it actually has variability. And one of the main ways of things that have variability is because of like plankton and phytoplankton and life in the oceans, that's the primary productivity. That's the base of the marine food chain. So it's really key in understanding that. And basically, it's blue versus green is what is used to discriminate chlorophyll, which is what's the relevant chemical for phytoplankton and for vegetation. So this is just an example. There's a relatively new sensor, just almost a year old now, the PACE, which is a NASA sensor, plankton, aerosol cloud, and ocean ecosystem. Modis also has, and Meier's also have can get ocean color data and detect phytoplankton. But PACE was designed specifically for that, or primarily for that. And so you can get really nice data and detailed data. This is the Gulf of St. Lawrence, and you can kind of see, these kind of swirling areas, the greenish areas, that's where you have balloons of phytoplankton there that it ballooned. There's a little bit of sea ice up here. This is from, April 23rd, 2024. So the sea ice, there's some remnant sea ice there as the spring is coming in. All right, so thermal infrared is basically greater than 1.3 micrometers. And that's again getting towards the more the peak of the Earth's emissions. That's what's being emitted by the Earth at its peak. And that's essentially heat when you get out to the thermal infrared. So we feel that and sense that ourselves as warmth, as heat. And the satellites can measure this and convert that into a temperature. And one of the areas that it's most commonly used is sea surface temperature. There's other ones that are used for filtering out things, but the primary ones are the 11 and 12 micrometers. So you can detect sea surface temperature. And one of the things that, sea surface temperature is of great interest. It's important for weather. El Nino is, detected through one of the ways through sea surface temperature and overall heat content of the ocean. And warming trends in the ocean is 70% of the Earth's surface. So temperature is very important. We have a lot of temperature records that go back along, hundreds of years because ships took temperature records. But there's a challenge in kind of matching those up because the satellite is measuring the emission, which is coming right from the very top of the surface, like the top millimeter to like just a really thin area. Whereas what they would do with ships, you dump a bucket in, and they're more sophisticated now, but they're still looking at, at least like 10 centimeters down below the surface. And, the surface is absorbing the sun's energy. The surface is going to be warmer than below. So you have to make some corrections if you want to connect that all together, which is very typical to do with satellite data versus in situ field data. So this is just the most recent one. This is, I forgot to put this on here. This is, I think, the MODIS sea surface temperature. And the tropics are warm. I didn't bother to show an example, but you can, the El Nino really sticks out when it comes in with the warm temperatures. You can't see the Gulf Stream. Again, it's, but you can see these eddies and swirls as the Gulf Stream, the warm temperatures that are extending far north due to the Gulf Stream. We can also use them on land and particularly for detecting fire. As we're all familiar with around here for sure with fires, but most recently the real devastating fires in Los Angeles. So this is from the 9th of January. This is a visible true color composite. So you can see the smoke there coming from the fires. And then those red dots are basically the thermal anomalies. It's basically looking for temperatures that are above what you would normally see at that location. And then it spotlights those. So these can be really useful. I mean, this was in Los Angeles, so everyone knew the fires were occurring. But in other more remote areas, this can be really useful for like, early warning and things like that, and just kind of detecting general trends in fire that may not have been, detected in the past. So, and essentially, again, it's just looking at heat, detecting heat. So we go into the microwaves.
Fire,
yeah.
please. Can you get like specific enough that they can like track where the fires are hottest and like kind of like compare internal to, or is it more like?
These data are like more like just detecting hotspots essentially. The data, the resolutions are like 250 meters. Well, actually in the thermal, it's more like 500 meters to 1,000 meters. So it's not super specific, individual pixels that it's seeing. I don't know how well they can you know, they can't really go beyond the pixel level. But I don't know how they can discriminate between, you know, one pixel or one grid cell next to the other, is what the exact temperatures are. I mean, they can get temperatures out of this. This product is just detecting like flagging, basically. This is on fire. So that's a good question. I don't really know exactly. Yeah. So microwaves, in the microwave of the Earth, we're detecting the emission from the Earth. So again, it's low energy, but it's very useful in the emissivity, which is the epsilon, is what the variable is. And it's really useful because it's very sensitive to the phase state of water, whether it's liquid or whether it's ice. And it also is sensitive to salinity, which is really good for like sea ice, for example. And it's dependent on the frequency of the microwaves or in the polarization, which I won't get into here, but it's basically a preferred direction of the emission of the emitted energy. And basically, you know, different objects have different emissions and different emissivity, and that varies based on frequency and polarization. So we can use that information to, you know, basically detect what we're looking at. And so sea ice is one of the things that we use, and everyone thinks sea ice is cold, but it's not. It's actually hot, and not just as a hot topic. It's because what we look at with the microwave emission, it's actually for at least a lot of the microwave, it's actually also dependent on the physical temperature and the emissivity. So we get what's called the brightness temperature, or TB, and it is a units of temperature, like Kelvin. But when you look at the emissivity, basically water has higher temperature, physical temperature is warmer typically, right? Than ice is, but it's very low emissivity. It doesn't emit much energy. And so when you look at the brightness temperature, the water brightness temperature is low. It's cold, 120 in this at 36 gauge, it's upwards of 120, 140 Kelvin, whereas the ice shows up really nicely there, and that's upwards of 250 to 280 Kelvin. And so you can, just looking at this map, you can pretty easily see where the ice edge is, at least in a general sense. And so it's counterintuitive when you look at the radiometric temperature, as we might call it, or the brightness temperature. Ice has a higher temperature than the ocean. There we go. So now, getting close to finishing up. Active remote sensing, and so that's contrasting to passive. And active means, again, as I said before, it's sensors providing its own energy. Energy is emitted by the sensor, interacts with the earth in some way, and reflects back to the sensor, and the sensor, that how much energy gets reflected back, how long it takes that energy to come back, and the type of energy tells you something about what it reflected off of. Types of sensors, we have the radar altimeter, laser altimeter, or LiDAR. That's ISAT2, or ISAT2 Atlas sensor. And then radar, which is basically an imaging. So it's not just detecting the reflection, it's actually detecting the variability of the reflection, then scatter from that. And a scatterometer is kind of a more general radar type of, it's in the radar range, but it's giving you more of a larger scale image. So ISAT2, we're probably a lot of us are familiar with that here. Work with the data somewhere or other, launched in September of 2018, and that's a photon counting laser altimeter, and sending out a laser down to the earth and bounces back. So it goes down, comes back, it's moving at the speed of light. And so basically, you know what the altitude of the satellite is, so then you can get the elevation of the surface or the atmosphere. It does bounce off clouds as well, so you can actually use it for clouds, but then you can't see the surface under that. And it's photon counting, which means it's sending out individual photons, and you can measure the actual photons, which can give you more information than just like looking at it as like a beam that bounces back. This is just an example. So this is a vegetation example that I grabbed from the ISAT-2 that I'm not exactly sure what this is. But basically the tan, kind of darkish tan line is the surface. Those are what's defined as the surface returns. The green is vegetation. So it's bouncing back somewhere within the vegetation, and then the real light tan there is the canopy top. That's what's defined. And then there's all these other ones that are there. Those are atmospheric ones that are filtered out, at least for this product. One of the things with ISAT-2, it's a laser, it's green laser, right? Yeah. And so, you know, the sun is emitting energy, and it's emitting photons, including green photons. So that has to be filtered out. So there's a lot of things that go into ISAT-2, and this will be one of the future talks will be on ISAT-2, so I won't go into too much more detail there. And then SAR, synthetic aperture radar, again, it's radar, sending out a radar pulse, sending it down. One of the things with radar and in microwave is the resolution tends to be fairly low because you're collecting information over a larger area to get enough of a signal. But SAR is kind of a specialized radar. What it does is it's using the motion of the satellite to kind of synthesize a bigger antenna. Essentially, you know, the antenna that you have that's collecting the energy, that helps define what the resolution is and limits the resolution. But with SAR, you can kind of, as the satellite's moving along, you're looking back and forward, and you can integrate that together and synthetically create essentially a higher resolution based on the energy as it's collected over time. And so, yeah, so you can, the thing with radar, it's nice. It sees through clouds and sees at night. It has its own energy, so you don't worry about sunlight. The radar signals go through clouds, so you can see the surface regardless of what the atmosphere is like. And you can see a lot of interesting things that's not visible. So yeah, it's a little bit weird to look at a lot of times because it may not look like what you're seeing, what you think you would expect to see. There's an example of the Black Rock City, the Burning Man back in 2011. But it's been used a lot is for archaeology. It can penetrate, like, for example, vegetation a lot of times, and you can see features that if you're on the ground or if you're on a plane just looking down or using a visible imager, you don't see anything. But with SAR, certain things can pop up that are like ruins that have been covered up, and that have a unique radar signature that doesn't show up in other wavelengths. So that's kind of cool. NISAR, which is the NASA Indian SAR, it's the next big SAR sensor. I did this originally, I think, back in 2018, and I had the launch was coming in 2020. But it is, as I understand, soon now. It's been long delayed for various reasons. I think I've heard as early as March it will be launched. And so that's going to be a lot of data coming in. That's into NASA. So for sea ice, it's also useful because it's microwave. So microwaves, which like passive microwave, it's dependent on the phase state of water, and so frozen versus liquid shows up. But SAR is kind of challenging to work with a lot of times. It gives you really high spatial resolution, which is important for ice, to like letting you track the ice edge. But it can be difficult to interpret. It's not necessarily, it varies depending on the character of the ice. It doesn't lend itself to simple algorithms, you know, simple little equations that you can just apply. It just doesn't work very well because the conditions are too variable. The oceans can roughen the winds can roughen the oceans and get a really bright return that is basically the same as what you see with sea ice. Meltwater can, you know, it's now liquid on top, and then how do you distinguish that? So it's pretty challenging, but it has been used for many years, several decades now, for ice charting, for navigational support. but it's been done through manual interpretation of the imagery and trained analysts that are looking at it and know what to look at. With your own eyes, if you look at it, you can recognize what you're looking at. You can understand like, oh, okay, this is melt, or this is, this is clearly ocean roughening. But it's hard to automate that. But there's been a lot of work, including by a couple folks here, looking at using artificial intelligence, machine learning approaches to do this. And that's, I think there's a lot of potential for that you could start getting more automated sea ice, as well as other things as well. But for our purposes, particularly sea ice, so that you could use this data. And for a long time, this wasn't as accessible as well, because it was a lot of it was commercial, and so you had to pay for it. So it wasn't freely available. That has changed quite a bit. And things like NISAR will be freely available. And like the Sentinel, which is European satellites, their data is freely available. So that's it. I did mention Java the Hutt, so I threw Java the reimagines episode 4 of Star Wars with Java in it. Yeah, any questions? Questions online. There's a chat. Oh, there's a question. Bruce Rout. Oh, oh yes, thanks, Bruce. Bruce, I neglected to mention the polar orbiting satellites. They're going over or near the pole. It's usually not directly over the pole. So that means they don't necessarily see the pole. It depends on how wide the swath width is. So a lot of the polar orbiting satellites have gaps at the pole. Like you mentioned, Astra and Landsat, the Pastor microwave have gaps at the pole where they don't see, because the sensor doesn't, the swath width of the sensor doesn't reach the pole. But places like things like MODIS have wider swaths, they do see the pole. So that's actually a nice thing to note there. So thanks, Bruce. And yeah, if anyone else has online, I think you can come off mute. You're welcome to do that. Any other questions here?
What is, I know there's like some commercially available, like Earth observation satellite. What is it? Could you like get all types of data out there if you're willing to pay for it, or like how do those compare to the like NASA?
So yeah, the commercial satellites tend to be, there are SAR satellites that are commercial. They tend to be, there's a lot of visible satellites, like Maxar, which is actually local here. And there's other satellites in there. They tend to be really high resolution and kind of focused on certain monitoring. They have flood monitoring where you want really high resolution, like street level, things like that. And so, yeah, they're commercial and they sell that data. There are certain agreements. NASA has like commercial small satellite data program. I forget what it's called exactly. Where there's some agreements to provide some data at no cost to the public. Sometimes, data that's real, like near time where they need it for operational support, it's valuable. People are willing to pay for that. But 6 months later, no one really cares about it. So then maybe it's made free, later on. That's not uncommon. Yeah, there's a lot of different commercial satellites, and then there's the military satellites, which we don't necessarily know a whole lot about. Some of that's been declassified over the years. There was a project Florence was involved with, I was involved with, that declassify some of the and release some of that, like I forget what the satellite was, but really high like resolution imagery, like centimeters of resolution, tens of centimeter resolution, and they in declassifying it, they dumbed it down. They made it degraded it, so it's not quite as good as what's really possible. But still, it was like meter resolution, so you can see individual flows of ice. You can see melt ponds, the little ponds of water on the ice, things like that. So it's really valuable for that. But those types of things, the data are, they're very large, and so they're oftentimes targeted for very specific areas. So, but yeah, good question. Yeah.
I'm curious about SAR data. You mentioned two, like archaeology and then sea ice navigation as applications. I've heard of like LiDAR for archaeology, but I guess I'm just curious about like, what is SAR really moving into as applications? Because people are starting to pay attention to it. I think it feels new to a lot of people.
Yeah,
I'm just wondering where it's
yeah.
used.
Yeah, I mean, its potential has a lot of potential for land applications. You can see different things. To some degree, I think some, the surface, characteristics, maybe vegetation, it's been used a lot for, looking at different, development. It's used for the ice, it's been used a lot on Greenland and Antarctica for detecting, the motion of glaciers and so that's another application. I know I'm not capturing all of them.
I asked you a big question.
Yeah, so, and I'm not familiar with, I'm mostly familiar with like the ice ones, but, it's really valuable because number one, you can see at night, you can see through clouds, so it's 24/7, coverage depending, as long as you're flying over an area, so it's really helpful for that, but it also is, it's looking at the microwave properties of, and so soil, soil moisture is one thing, SMAP. Originally, it's soil moisture active, passive, it originally had an active radar on it. So in combining that with the passive, you could really do a really nice job, so that's another area, soil moisture, certainly. And so, but I think it's still kind of an emerging, in some ways, I mean, it's been around a long time. RadarSat-1, which was the Canadian, that was launched in like 1995. I think that was the first real widely used SAR. And that was commercial. But so that's 30 years ago though, so it's been around a lot, but I think it's still, like I said, there's a lot of people that are kind of discovering it. It is challenging to work with. I mean, part of the reason, it was a lot of it was commercial, so it was expensive. You couldn't really get it. And I mean, literally, if you wanted like a 500 kilometer by 500 kilometer scene, it would cost you like $3,000. So, it was not something you did. The average person or even, your average educational or researcher could afford. But now it's becoming more open. So that's one of the things. And I think there's just, more realization of the value of it. But it's also challenging to interpret. So it takes some understanding, expertise, and like I said, for sea ice, it's been somewhat limited because it's just, you can't just throw it into an algorithm and spit out sea ice concentration, or you haven't been able to. But with machine learning, we probably will get there before too long. Yeah. Any other questions? Anything else? Oh, Tosh mentioned, I'm always curious about ethical concerns over remote sensing, especially when it comes to sensing heritage sites or ruins. That's a really good point. I mean, that's not something I'm super familiar with, but these are, these sites can be, culturally sensitive sites, and you're collecting data from them, even from afar. There are ethical concerns about that. There's certainly ethical concerns about, looking at people's houses and where they live and things like that, just more generally, even with like Google and things like that, but I'm not too familiar with, those discussions. I know I've heard of them. I think they're important. But I don't know, where things stand. But that's a really good question. Thanks, Josh. I think that's it. Any other questions before I finish up? Okay. Thank you. We'll see you next week. And around a month from now, hopefully.